Hello, and welcome to the second in the video lecture series on chemistry presented by me, Mr. Ralstin. Today's lecture is measurement in chemistry. Why is it important? What are some of the units we'll be using? And a little bit on the SI system, which should be fairly familiar to you at this point. Let's get started. So what is measurement? Measurement is the act of assigning a numerical value to an observable quantity. Now, that's science speak. In reality, measurement is just looking at something with a tool that has numbers and attached to it, such as a ruler, a graduated cylinder, scale, anything we might use in the lab that has numbers attached to it is a measurement tool. And a measurement is when we use that tool to get a measurement of the quantity. In chemistry, like all the sciences, it's very important we use the SI system due to its not only its simplicity, but its universal nature. The SI system is the same everywhere, whereas here in the States we use the English system, which is just a giant mess. So keep that in mind when we're doing measurements. In our system of measurement, we use several base units. These base units are the only things from nature we can calculate or we can read while doing no calculations. They can be taken directly from the environment. There's no need to combine or calculate or measure anything but these actual properties. And there are 7 of these in the SI system of measurement. They are the ones we are probably most familiar with, and here they are. First and foremost, time, and time's difficult. Time's hard to describe, and if you can in the future, just sit down and try and describe the definition of time to yourself. It's impossible, because time is just a fundamental quality. It's something everyone understands. Time is defined by its measurement. We don't really have a way of moving through or back and rewinding or moving in different places in time, so we can only define it by measuring its passage. The base unit of time in the metric system is seconds, which are the same seconds that are on the clocks we use to tell time, so shouldn't be any difficulties there. The second unit we're going to talk about is mass, and as you can tell, this, let me find my arrow, this is a very large mass. A very large mass. So large, in fact, that you would think this guy right here, these people, they should be crushed. Ah! But enough of the joking. Mass is the amount of matter in a substance. The standard SI unit we use in chemistry to measure mass is the kilogram, though in our laboratory setting we will more often use the gram, which is smaller, and our instruments more easily read grams than kilograms because of that. The next quality we're going to discuss is electrical current. You know, you stick your finger in the light socket and you get shocked. That's electrical current. The amount of electricity running through a circuit is the actual definition of an electrical current. There's a battery, there's a wire, there's a resistor, all that stuff that you'll learn in physics. But the standard unit for current is the ampere, or amp for short. We don't use amperes in electricity very often here in the chemistry lab, but it is still important to know that this is one of the 7 base units we can measure. You also have length, something all of you are very, very familiar with. How tall are we? How big is our foot? How long is a foot? How long is a mile? 5,280 feet, etc., etc. Length is just defined as the distance between 2 points, and the SI unit of length is the meter. Not the foot, not the yard, not the mile, the meter. This is about the equivalent of a yard. Actually, a yard's a little shorter than an actual meter, but it is what it is. So we're pretty familiar with length and its purposes. Luminous intensity is one we have an innate understanding of, but don't really think about very often. Luminous intensity is how bright something is, and we usually use the sun as a comparison just because the sun's constant. You see it the same everywhere. It's the amount of daylight we have. And the standard unit for luminous intensity is the candela, which, if I remember correctly, is based on the intensity of the sun. I'm not sure if it's one candela is the sun, but I do know the intensity is based on that of the sun. So, temperature is another of these standardized units, and we all know what temperature is because whether we'll admit it or not, we were all that kid who touched something hot when we knew it was hot and we didn't want to, or our parents told us not to, excuse me. Temperature is the average kinetic energy per molecule of a substance, and it's typically measured through heat transfer because we can't take and measure each individual molecule, so we can only get an approximation based on the heat transfer. In the metric system, we do not use Fahrenheit, and believe it or not, we're not even supposed to use Celsius, though we do for our practical purposes because it is scaled more to what we're used to. The standard unit for temperature is a Kelvin, which is based on absolute zero. 0 Kelvin is absolute zero, whereas room temperature would be about 293 Kelvin. It's a big number to use, so that's why we use Celsius, and room temperature is about 20 degrees Celsius. The next unit we're going to talk about is the one that you will most certainly become very familiar with here in the chemistry classroom. That unit is the mole. Not mole as in the guys that dig in the ground, or mole as in the informant who disguises himself and is playing double agent. No, this mole is 6.022 times 10 to the 23rd, which is why my little chemistry cat is joking. Got mole problems? Call 602-1023. The mole is the amount or the number of items in a sample. The standardized count for a mole is 6.022 times 10 to the 23rd molecules. So 1 mole is equal to that many molecules. We use that amount because when we apply that number to the atomic mass of elements, it actually works out very nicely that 1 mole is a nice round number for elements, and that will become more clearly when we get into dimensional analysis and stoichiometry. Just as a review, here are the base units. Each of them we've talked about. The meter for length, the kilogram for mass, the second for time, electrical current, temperature, luminous intensity, and the amount of substance. Just to give you an idea, we will be using in this class primarily the kilogram, the second, Kelvin, and the mole. While meters occasionally play a role, they are very rarely used in chemistry because they are such a large number, and they typically have to do more with the physics of motion. In chemistry, we're looking at reactions and the matter itself, so we typically deal with the mass, the time, temperature, and the moles of those substances. And then, in addition to our base units, you also have derived units, and derived units can't be measured directly from the environment. Instead, they have to be mathematically crunched. You have to apply more than one base unit together to get the derived unit that you're using. In chemistry, we will use joules, which are here, pascals. Occasionally, if we get to electrochemistry, we might use the volt and the farad. We definitely will use the frequency, which is hertz. And then you're probably already familiar with newtons, which is right here. But in general, once again, chemistry is a science devoted to matter, whereas Newton is more of a physics concept, so we won't be discussing it much. Metric prefixes. As I mentioned, the measurement system we use here in chemistry is based on the metric system or the SI system. They two don't mean the exact same thing, but they are synonymous because the new SI system is based on the old metric system and its base 10 principle. The metric system is very, very simplistic because in order to increase or decrease the size of the unit of measurement you're using, all you have to do is divide or multiply by a power of 10. This allows us to improve both precision and accuracy when we're doing smaller or larger measurements. For example, if we're measuring the length of a pen, you probably want to use centimeters. If you're measuring the length of a room, you want to use meters because it's a more precise measurement. Just to give you an idea of some of the metric prefixes that exist, here's a big list of them. The largest that on this list is the yada, which we will never, ever, ever, ever use. And the smallest is the femto, I believe, if you can see it at the bottom. No, excuse me. The zepto? Yes, I think the zepto, unless my screen's cutting one of them off. However, we don't deal with these large numbers very often. And if we do, we're still dealing with them in regards to what you probably are familiar with. We use this range right here from milli up to kilo. We don't use very many others, though occasionally I might mention a giga or a tera or a nano or micro as well. These are smaller units or larger units in the case of a giga and the tera, but primarily we use these guys because those are the ones we use in real life. And of course, since we're talking about measurements and we're talking about metric prefixes, it only makes sense that we talk about how to perform measurements and how to do them not only with precision but accuracy. What you're seeing on the screen right now is a graduated cylinder. Now, take a few seconds and try and read that cylinder and write down a number for what it should read. Now, a lot of us, especially if you've not had a science class before, probably read from right here, where my blue line is at. That is incorrect. Now, I understand why you might want to look there, because that is the highest line you see. However, water has this thing called cohesion, which you probably learned about in biology, as well as adhesion. So it forms this little meniscus, which I'm going to draw in red. See right here, this little curve. Now, you can't really see to read it, so I'm going to have to erase it, but that's what we're looking at. Oh, wrong button. There we go. There we go. So, let's switch to, here we go. So we're looking at this line right here. There we go. That's a better tool to use. All right, so if you look at that line and try and read this, you need to do so with a consistent manner, and that's why we use this meniscus, because this meniscus is always consistently the most accurate position. If you read up here at the blue line, sometimes that moves based on the type of water or the compounds in the water. This distance from here to here might vary. That's why we use the meniscus. Now, this meniscus, if you look at it, is definitely 6 milliliters, but it's 6.2, 6.4, 6.6, then you get to 6.8, and that goes farther. So, for sure, you are going to write a measurement of at least 6.8. However, that measurement is not right on the line. It's kind of between, but it's not quite at half. So you need to add an additional number. I would call that 6.83 as my measurement. Now, when you're taking measurements, you need to choose a system and stick with the system. That way you are consistent in your measurement. Well, and there's a reason for why we should be consistent. Because we need to be accurate and we need to be precise. I would much rather be a precise scientist than an accurate scientist because I can always calibrate my precision to be accurate. But if you're inaccurate, then you're just inaccurate. Over here, the top left, up in the top left, you'll see the target that it has low accuracy and low precision. Accuracy is how close you are to the bullseye. Right here. This is where we want to hit, right? I mean, we've all gone target shooting before, and if you haven't in real life, you at least understand the concept. You want to hit the bullseye. So you want to be accurate. You want to be close to the bullseye. But if you look at the spread, all of his shots are way off, except for this one right here. Way off, way away from that bullseye. So he's not accurate. And not only are they way off, they are not grouped well, so they're not precise, which means it's not an easy fix to get close to that bullseye. On the other hand, over here on the top right, you've got a very precise grouping. This person hit the same spot all 6 times. They weren't accurate because they weren't close to the bullseye, but for sure they were precise because all the grouping is very close to each other. Over here, you've got high accuracy, but low precision. All the numbers are close to the bullseye, but they're not grouped close together. So it's high accuracy, low precision. And then this is, of course, the ideal. High precision, high accuracy, hitting the bullseye every single time. Now, if you're in the chemistry lab, you would much rather be precise, and precision comes down to your skill and how you read the instruments. Accuracy, your instrument could be wrong, or you could be reading it slightly wrong that's giving you wrong numbers, but you're reading it the same way every time, which makes you precise. We can do a little math and fix this into this in the chem lab, so you much rather be precise than accurate, if you had to choose. Okay, so that concludes our lecture on measurement. Next time we will apply the concepts of significant figures to the numbers we measure. Now, sig figs are fun once you get the hang of them, but they are difficult at first, so be prepared to watch, rewatch, and hopefully not have to relearn. Thanks. See you next time.